Next talk will be about programming with projective Cliffords by, let me know if I mispronounced this, Jennifer Paykin. By the way, there will be a picture after the end of the talks. Were you just saying, can we get, oh. Yeah, there will be a group picture, so stay around until the end of the session. And for a little bit after that, we will line up against one of these walls. Okay. Sure.
Okay. All right, thank you. All right, so I'm going to be talking about some work that I've been doing with Sam Winnick, who is here as well, which I'm very excited about. So I'm going to talk about Cliffords, except that this, okay, there we go. Okay, I'm going to talk about Clifford operators. So from the gate perspective, right, we've all seen Cliffords as those circuits that are generated by, well, there might be different sets of gates, but one such gate set is the Pauli operators, X, Y, and Z, along with Hadamard, S, and C naught, for example. But of course, this is not how you define Cliffords as unitaries. They are defined as exactly those unitary matrices that take the Pauli group to itself by conjugation. So here I'm talking about for any n-qubit Pauli, so that is roughly a tensor of the single qubit Paulis, U dagger is also in the Pauli group. Okay, and so what I want you to think about is how Clifford forms a function on that Pauli group, right? It takes the input P to the output U dagger. This function is called a projective Clifford, and indeed, any such function, specifically a center-fixing automorphism on the Pauli group, does characterize an equivalence class of Clifford matrices. Right. So here's my proposal. I want a language where I can write functions over the Pauli groups and a type system that says that well-typed functions are exactly the projective Cliffords. I would like this to be a pure lambda-calculus with a very nice simple operational semantics, ideally. I would like this to be compilable to circuits. And I would like this to show us new ways of thinking about how we use Cliffords and what they're doing for us in our quantum algorithms. So projective Cliffords are not a new idea, right? If you've ever used Pauli tableaus, or sometimes called Clifford tableaus, also called Pauli frames, you have seen these. You are working with projective Cliffords. So Pauli tableaus form the backbone of how we do efficient simulation of stabilizer circuits, and they're used in, they can be compiled, synthesized to physical circuits, and they are also useful in optimization. But they're not a language. They tend to look like this, as like a bit vector encoding, and sometimes you can write this in a little bit of a more readable way that looks something like this. So this is a 2 by n table, a tableau, where the sort of table entry, the sort of matrix entry is really encoding this table here. So in the ith row, the left entry describes the action of our Clifford on x sub I, and in the right row, it describes the action of our Clifford on z sub I. And because x sub I and z sub I for every I form a basis for the n-qubit Clifford, the n-qubit Pauli group, it suffices to just give these entries to define our function, right? So, okay, let's write this in a more functional style. Oh, I seem to have messed up my Okay. I don't know what's going on up there with the text, so sorry. Okay, so here is a representation of that same projective Clifford from the previous slide. But I'm adding some complicated syntax. So let's take a look at what this is saying. So I'm writing the type of C0 as a function from this Pauli.Pauli to Pauli.Pauli. So here, when I write Pauli, I mean a single qubit Pauli. And then Pauli.Pauli is the 2-qubit Pauli group. I'm defining this function by pattern matching in kind of like a Haskell style syntax, pattern matching syntax. And so I'm writing these brackets for this pattern matching syntax, which is really just pseudocode. Sorry for the interference. And then I am also writing, you can see I'm writing in 1x instead of x1. That's just so that it's more textual. And I'm also writing this star for approximately matrix multiplication. It's really matrix multiplication up to a phase, but it satisfies x star z is equal to y. Anyway, you can think of it as matrix multiplication. Okay. So as we said, since we have the action of this function on the basis elements, we can compute the action of this C0 Clifford on any Pauli in the 2-qubit Pauli group, right? So let's consider an example. How does C0 act on Y1, for example? Well, to answer that question, we're going to compute in our language. So if we apply C0 to in 1y, what we're going to do is break up that y into its basis elements in the Pauli group. Okay, so that's in 1x star in 1z, as I said by the definition of star. Our projective Cliffords distributes over this star operator, and then we can simply do the substitution for the basis elements and simplify as a result. Great. So our answer, if I haven't done anything wrong, is y1 x2. Okay, we can also take these functions as I've written them down in this functional style and compile them to circuits just by reusing the techniques that we already have for Pauli tableaus and Pauli frames. So we can easily apply this function to our 2n basis elements of the n-qubit Pauli group and get a tableau out, and then use existing tools like PCOAST, which is an Intel product from our compiler toolchain, but there's lots of other tools as well to obtain a Clifford circuit. Okay, so great. I introduced some syntax and made it look a little bit more like a function, but so what? This is not anything new, right? Well, let's look at what we can do when we take this programming perspective. So for one, we can define polymorphic functions, right? So here's a swap operator that operates on any combination Pauli group type. So it takes any t1.t2 to t2.t1, and it just takes in1q to in2q and vice versa. Okay, great. Here's another example. Any Pauli p on that top row is itself a Clifford operator, right? And we know that because p dagger is plus or minus 1q. So it's another Pauli in the Pauli group. And the exponent of the minus 1 is, I'm writing it omega. This is the symplectic form that encodes the commutativity of the Pauli group. So I'm going to write a function, Pauli to Clifford, that takes some Pauli type t and outputs a Clifford from t to t. And what this Pauli to Clifford does is returns q, so the input to our Clifford, with some phase. So this bracket syntax is exactly introducing syntax for that phase, that plus or minus 1 scalar. Okay, I'm going to give one more example, which is a bit more involved, but I don't necessarily want to convey every single detail, more of the general idea, and then the details are in our extended abstract. So let's talk about the Steen code, which is a stabilizer code. And the way this code works for error detection and correction is that we have, we're encoding one logical qubit in data qubits. Those are the green D1 to D7. And then we use 6 stabilizers and 6 ancilla, where each ancilla is going to be used to compute the measure the stabilizer, right? So when we do these measurements of the 6 ancilla, we are going to get out a series of bits, and then we can decode those using the Hamming check matrix there. So I won't go into the details of exactly how that works, but I will show you what this looks like in our Projective Clifford programming style. So let's just concentrate on the non-grayed out parts. So I'm going to start by, this is a little bit hand wavy, but defining a Pauli data type that describes the Pauli group that this Steen code is operating over. So the Pauli group that it's operating over is inherently a 7 for the 7 data qubits plus 6 for the 6 ancilla. So it's a 7 plus 6 size Pauli group, right? I will say that these the ancilla are sort of naturally broken up into the bit flip ancilla, which detect the bit flips, and then the phase flip ancilla, which detects the phase errors. Okay. So this Pauli data type is going to be what our Steen code, the specification of our Steen code, right? It takes a Steen type Pauli group to a Steen type Pauli group. And what I want to point out is that in these different branches, this projective Clifford takes what is essentially Z sub A for the ancilla qubits to one of the 6 stabilizers. So whichever stabilizer is being measured to that particular ancilla. And then the Steen, and then this projective Clifford takes the X sub I and D sub I for the data qubits, and describes how we like decode the syndrome that you got out from those measurements. Yeah, okay. So again, this is very high wavy, hand wavy, but I just wanted to illustrate. My talk is called Programming with Projective Clifford, so I want to try to give some idea of what it looks like to do this programming with Projective Cliffords. Now, in the paper that we have, we actually give, of course, the full details of the type system that encodes that checks the property that the particular functions that we're writing down actually do correspond to Projective Cliffords. So, because of course, I only showed you functions that do make sense, but there are plenty of functions that you can write down in that same style that do not correspond to Projective Cliffords. So we need a type system to tell us when that is okay. So very briefly, I'm going to give an overview of the different components of the type system. I'm not going to show the rules and the details. Again, there's a paper for that. Okay, so what are these components of how do you know that a function is a projective Clifford? A function from Paulis to Paulis. Well, to start off with, it needs to be a group homomorphism over the Clifford group, as we said. Sorry, over the Pauli group. And so that property of being a group homomorphism, it really corresponds to linearity in the sense of linear transformations. In fact, we can enforce this property using a linear type system, or more specifically, a linear algebraic type system in the sense of there's several papers by Alejandro Diaz-Caro and Gilles Dawek and some others. So these are similar type systems, although not exactly the same, that let you add and scalar multiply essentially vectors in a lambda calculus. Okay. So that's one step, is a sort of linear algebraic type system. Step 2, which is sort of the core restriction on these functions, is that they need to respect the symplectic form. Now, I briefly mentioned that the symplectic form is this function omega that encodes the commutativity of the Pauli group. So, right, PQ is plus or minus 1 QP for any two Paulis, P and Q. And we can define this function omega as just a linear transformation. So this is not a Clifford, this is just a linear transformation on the basis elements x and z in a straightforward way. Now, every projective Clifford needs to satisfy the property that it needs to respect the symplectic form. So omega of f of p and f of q, it needs to be equal to omega of p and q. So we enforce this property using what we call a symplectic type system that when we do pattern matching checks that this property holds for each of the different branches. Okay, and there's one more component, which is that the phase that I talked about a little bit before, you have a plus or minus 1 phase, that also needs to be a linear transformation from the input Clifford. But luckily, we already have a linear type system, so we're able to incorporate it through that. So the details can be found in our preprint on archive. We call this lambda-calculus LambdaPC for projective Cliffords. And it includes, several details. So we have a type system, an operational semantics, and a categorical semantics that we prove are all sound with respect to each other. We also have a companion paper that actually establishes that the properties that I showed in the previous slide, so the properties that we need the type system to enforce, or rather the category, the categorical semantics, those are actually the correct properties. Specifically, the linear phase function, it's not necessarily straightforward that this is the property that you need to hold in order to characterize the projective Cliffords. And in fact, the reason why this is so fiddly and tricky is because we do this not just for qubit Cliffords and qubit Paulis, which is what I've been talking about in this talk, but in fact for qubit Cliffords for arbitrary d. So this is very, these projective Cliffords are very well understood for d equals 2, which is qubits. And they're also very well understood for odd values of d. But for arbitrary even values of d, the details are actually quite fiddly. So it's very nice that we're able to capture all of those details in one coherent system. Okay, so I'm almost done, but I just want to wrap up with one reflection, which is why do we care about Cliffords? Cliffords, they're not even universal, right? Like, you can't write, they're classically simulatable, so why would you bother writing about them? I did look up, by the way, and this is William Clifford. Okay. Well, why Cliffords? So these encodings of Paulis and projective Cliffords are used all over the place in software toolchains. So including the PCOS toolchain that I referenced before, as well as lots and lots of others used for optimization and synthesis and all this. So that's one reason to understand it better. But there's also, I think, some really interesting extensions about how we might extend this kind of Clifford Pauli-based programming into a universal language. So we can think about mixing qubit Cliffords of different dimensions, and suddenly, a qubit quantum Fourier transform for d equals 2 to the n is, somehow the same as, a qubit Hadamard transformation for d equals 2 to the n is somehow the same as quantum Fourier transform for n qubits. So by mixing these different qubit Cliffords, you sort of get additional computational power. We can also think about the projective Clifford hierarchy and use this as a framework to study that. So that said, thank you for listening to this very high-level introduction to how you might want to think about projective Cliffords.
Okay, we have time for a few questions.
Thank you so much for the talk. Could you briefly talk about this mixed dimensional case? Like, how did your type system, it fixes the dimension of each qubit that you have in the system. And then how did you define this, like, the Clifford group for, the Clifford hierarchy for your mixed dimensional cases?
So these are two different points, the mixed dimensional and the Clifford hierarchy. And they're both future work. So I won't speculate too concretely about it, but the mixed qubit Cliffords, according to my co-author, we can form a group that is consists of, I think, the inner product.
Well, you form like the central product.
The central product of the Paulis of the different dimensions. So there is mathematically a foundation for combining these different operators. Yeah.
Thanks. I'll ask you about it offline. Because
Great.
Thesis is doing like 3 months on qubits.
Okay, very nice. So to return to your question about is your Clifford a projective Clifford, and you put in all kind of type systems and things to settle that. I suppose that you got all your favorite projective Cliffords to type check, and it's not hard. The types don't get very big and stuff like that.
So the types don't get big. So I will say this was all pseudocode that I showed.
Yeah.
I don't know if I was clear, but we don't have an implementation right now.
Yeah.
So we can check the types by hand, and we've done that for a variety of examples that we thought of, and yes, there is no problem. The algorithm, the type checking algorithm, we have not yet explored the best way to make that an efficient algorithm. So right now, it in the worst case, it could explode in terms of the number of branches.
I see. So checking whether a Clifford is a projective Clifford, is that a decidable problem or is it an undecidable problem, or do you know?
If you have the unitary representation, you just need to check its action on the 2n basis elements of the n qubit Pauli group.
Yeah.
So you do a bunch of matrix multiplications, and you see if the outputs are also in the Pauli group. So yeah.
Okay, so an exponential amount of effort, but it can be done.
If you're doing matrix multiplications, then yeah.
All right, let's thank our speaker again.